In chapter 11, we cover the chi-squared distribution, and the chi-squared distribution is used for two different things. The first thing we use the chi-squared distribution for is to check how good a fit the data that we collect is to what we expect. An example of this would be, let's say, the M&M test that we did earlier this semester. Mars has data that says that the distribution of colors in a bag of M&Ms are expected to be, and it gives you the data. Now you can open a bag of M&Ms and count the number of colors you get of each color and find a frequency, a percentage of the total of that color, and you can compare it to what Mars says is true. So, is what they say actually true, that it actually fits that particular percentage, or does it not fit what they say? So, that's the first way you can use it. And the second way you can use it is to test independence. So, you have two variables that you think are related to each other. And you can test whether or not there actually is a relationship between those two variables. And that is a chi-squared test of independence. So you can use the chi-squared for a goodness of fit. How well does the data fit what I expect it should be? And second, are these two variables dependent on each other? Is one dependent on the other? And I can use a chi-squared test of independence. And I am going to quickly skip through the introduction here. You can read through that if you want. And I'm going to go straight to the goodness of fit test. Um, the null and alternative hypotheses for this test are usually written in sentences, or you can state them as equations or inequalities. And here's what's important: the goodness of fit chi-squared test statistic. And to calculate the chi-squared test statistic, you do this calculation. And what this calculation says is, okay, you've got data that you've collected. Those are your observed values. So you have that bag of M&Ms that you've opened up and you've counted the various colors. You actually have that data. That is what you've observed. Mars has data that they say that the distribution of colors should fit. That is what you expect. So what Mars tells you is true is what you expect, and what you observe is what you actually observe. And so you take this observed data, you subtract what you expect, and you divide it by the what you expect, and then you sum those all up. And you'll see what we mean when we do an example. The observed values are the data values, and the expected values are the values you would expect to get if the null hypothesis were true. There are n terms of the form O minus E squared divided by E, and this is called the squared Pearson residual. So if any of your homework, it comes up and says, what's the squared Pearson residual? That is what they're looking for. Now, here's the sticky part down here, the degrees of freedom. The degrees of freedom are the number of categories minus one. So if in a bag of M&Ms you have 5 different colors, then the degrees of freedom would be 4, the number of categories 5 minus 1. The expected value for each cell needs to be at least 5 in order for you to use the chi-squared goodness of fit test. Okay, so let's do our first example. Absenteeism of college students from math classes is a major concern to math instructors because missing class appears to increase the drop rate. Suppose that a study was done to determine if the actual student absenteeism rate follows faculty perception. the faculty expected that a group of 100 students would miss class according to. Now, whether this is experience or what, they have determined that half of the students will miss 0 to 2 classes, and they expect a third of the students, 30 out of 100, to miss 3 to 5 classes, etc. So this is what they expect to see, and we're going to actually look at what they actually find out. Okay, now we have a problem here. 12 plus days, we only have 2 students. And to be able to use the chi-squared goodness of fit test, we need a category to be 5 or more. So we're going to end up having to combine the 9 to 11 days and the 12 plus days into one category. So this is going to end up being 9 plus days, and that category's frequency is going to be 8. We can't do the goodness of fit test when we have a category that's 5 or less. Okay, now here's what they actually observed. So what they actually observed during the semester was 35 of the students were gone 0 to 2 days, etc. And again, we have the same issue that we had before. So we're going to combine the 9 to 11 and the 12 plus to get 5. And the category is now going to be 9 plus. Okay, so here's how it turns out. So we have 0 to 2 days, 50, 3 to 5, 30, 6 to 8, 12, 9 plus is 8. This is what we expect from whatever, the instructor's history, what they feel, whatever. This is what they would expect. And here's the actual observed values. So do the observed values actually fit what they expected? Is there a goodness of fit between this data? Okay, so now we need to calculate our squared Pearson residuals. So we're going to take each one of these observed values. We're going to subtract the expected. We're going to square that, and we're going to divide that by the expected. So we're going to take our observed value, 35. We're going to subtract our expected, 50. And we're going to square that, and we're going to divide that by the expected, which is 50. And we just take out our handy dandy calculator and we calculate that, and I get 4.5. We're going to do the same for the rest of the categories. So 3 to 5 days, 40 minus 30. I'm going to square that and divide that by 30. So that's going to be 3.333. Okay. And then we have observed minus expected, 20 minus 12, squared divided by 12. And I get 5.33. And then observed minus expected, 5 minus 8. We're going to square that and divide that by 8. And you'll notice that these always turn out to be a positive quantity because you're squaring that observed minus expected. And whenever you square a real number, the result will be positive. So that's going to be 1.125. Okay, and I add that column up. The sum of the squared Pearson residuals, that sum is the chi-squared. So chi-squared is equal to 14.291. So my test statistic which is chi-squared, is equal to 14.291. Okay, so now we need to look at what is the probability if this is true, that what I expect is true. What's the probability of me getting a chi-squared of 14.91291 or greater. So this is the p-value. What is the probability that I get a value that extreme or more if my observed and my expected are actually the same? Okay, so we're going to go find the chi-squared distribution in our distribution menu in our calculator. So let's go over to our calculator. And I'm going to go to my distribution menu, which we haven't used in a while, but the chi-squared is number 8. So a chi is the Greek letter chi, and it kind of looks like an X, kind of a squiggly X, but it's number 8. Okay, so we're going to put in our lower bound, which was that 14.291. And the upper is infinity, 1 times 10 to the 99. And then the degrees of freedom, we had 4 categories. So the degrees of freedom is 4 minus 1 or 3. And we get 0.00255. So that is the p-value. The p-value is 0.0025. That's a really low p-value. If the p is low, the null must go. So the p-value was 0.0025, which is low. So if the p is low, the null must go. So we're going to reject the null hypothesis. So there does not, the data that we observe appears not to follow what we expected. So based on the data that we've collected, we would assume that they actually are not the same. So our decision is to reject the null hypothesis. At a 5% level of significance from the sample data, there's sufficient evidence to conclude that the number of days students are absent do not match the faculty perception. Okay, I'm going to go back and I'm going to do this again, and I'm going to use the chi-squared test. There is a chi-squared test on your calculator, and I'm going to show that to you. So let me go back to my calculator, and I'm going to go to my stat and my tests, and I'm going to scroll down through my tests, and there should be a chi-squared goodness of fit test, and there it is, the chi-squared goodness of fit test. And if I conduct that test, I'm going to go ahead and hit enter. If I conduct that test, you notice that I have to put my observed values and my expected values in a list. So I actually have to put observed in one list and expected in another list, and then I can conduct this test. So let's get out of here. Let's go back to stat. Let's go to edit, and let's put that data in. It looks to me like I need to clear out some data. So I'm going to do this all in one big fell swoop because there's so much. I'm going to clear all my lists, number 4. And now we can go back in and put that data in a list. So I'm going to put the observed in L1 and the expected, what the teachers thought it should be, in L2. So we had 35 we observed, and we had 40 we observed. Well, if I can type it in. And then we had 20, and we had 5. And now I'm going to put what I expected, what the teachers expected in L2. So they expected 50 for the 0 to 2 days. They expected 30 for the 3 to 5 days. They expected 12 for the 6 to 8. And they expected 8 for the 9 or more days missing. Okay, and now we're going to exit out of our lists. we're going to go back in our stat menu over to tests, and we're going to run the chi-squared goodness of fit test. And I put my data in L1. That's where I put the observed. I put the expected in L2. And the degrees of freedom is 3 because we had 4 categories. 4 minus 1 is 3. So let's calculate that. And you'll notice I get the same answer. Well, I'm off by a 10,000th. I'm off by 1,000. So it's more accurate here because I didn't round off. When I was doing the observed minus expected, there I rounded off, so I got a little bit off on my chi-squared. But the p-value is the same, 0.0025. So again, I'm going to reject the null hypothesis. There appears to be that the teachers were incorrect about what they expected. Now I want you to look at that last row there. The last row, this CNTRB, and I actually do not know what that stands for. I should probably Google it. But this row right here are your squared Pearson residuals. So this is O minus E divided by O minus E squared divided by E. So you remember on our slide, when we took O minus E and we squared it and we divided by E, we got 4.5. And if I just arrow over, I can see all the squared Pearson residuals. So if you don't want to calculate them, your calculator will calculate them for you using the chi-squared goodness of fit test. Okay, so let's do another one. Employers want to know which days of the weeks employees are absent in a 5-day work week. Most employers would like to believe that employees are absent equally during the week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The results were distributed as in the table. For the population of employees, do the days for the highest number of absences occur with equal frequencies during a 5-day work week? So in other words, in a 5-day work week, if you ask 60, they would expect every day that there were 12 to be absent. So they expect the same frequency for every day of the week. So you'd have 12 absent on Monday, 12 absent on Tuesday, 12 absent on Wednesday, etc. So that's what we would expect. So our null hypothesis, which I should have written down on the previous problem, our null hypothesis and our alternative hypothesis is that they occur with equal frequencies. I'm going to be very abbreviated here, equal frequencies, and that they're not. Okay, so equal frequencies would be 60 divided by 5, which is 12. So our expected values each day of the week, Monday, Tuesday, Wednesday, Thursday, Friday, what we would expect is 12. What we actually observe is on Monday 15, on Tuesday 12, on Wednesday 9, on Thursday 9, and on Friday 15. So we can calculate the chi-squared residual if we want. Probably should make this up a little bit higher so we got some room. So this is 15 minus 12 divided by 12. 15 minus 12 squared divided by 12. And this is 12 minus 12, which is 0, by the way. And then we have 9 minus 12, squared divided by 12. We have 9 minus 12 squared divided by 12. And we have 15 minus 12 squared divided by 12. So our squared Pearson residuals, and for some reason on this particular problem, I used fractions. I'm not quite sure why I did, but I did. So I had 9/12, 0, 9/12, 9/12, and 9/12. So the sum of this is 3. So the chi-squared test statistic is 3. So we can go run the chi-squared distribution. What's the probability that we get 3 or more? Excuse me. So I'm going to go to my distributions, find the chi-squared distribution, number 8. My lower is 3, my upper is 1 times 10 to the 99. I had 5 categories, so the degrees of freedom is 4. 0.5578. That's a huge, huge p-value. So if p is high, the null must fly. So the p-value that we got is 0.5578. So that's huge. So we don't reject. The data is not statistically significant enough to say that what we observe is actually different than what we expect. The decisions not to reject the null hypothesis at a 5% level of significance from the sample data, there's not sufficient evidence to conclude that the absent days do not occur with equal frequencies. Now, again, we can do a chi-squared goodness of fit test if we want. So let's go back to our calculators. If we don't want to run the chi-squared distribution, we can do a goodness of fit. And to be able to do that, I need to put my observed and my expected in a list. So I'm going to put my observed in L3. So Monday we observed 15, on Tuesday we observed 12, on Wednesday we observed 9, and on Thursday 9, and on Friday we observed 15. And what we would expect if is equally distributed throughout the week, if absentees are equally distributed, we would expect 15 for each day. Okay, so now we're going to go run a chi-squared goodness of fit test. So go stat, tests, find the chi-squared goodness of fit. I put my observed in L3, and I put my expected in L4. And I had 5 categories, so my degrees of freedom is 4. What did I do wrong? Watch me do this in real time. What did I do? Something I did wrong. I either put my data in wrong or I ran the test wrong. So let's find out. What did I do wrong? 15, 12, 9, 9, 15. Oh, L4 is completely wrong. If I take 60 and I divide it by 5, I think I get 12. So my second list was entirely. Okay, try this again. Okay, now it should be correct. So the chi-squared test statistics is 3, and there are my squared Pearson residuals, 0.75. They're all the same, except the second one is 0, 0.750, and the rest of them are 0.75. All right. And the previous slide, I kind of zipped right through it. It's just what I've been telling you about running the goodness of fit test. One study indicates that the number of televisions that American families have is distributed. This is the given distribution for the American population. So the population on a whole is expected to be this. Okay. They randomly observed 600, well, they observed a random sample of 600 families in the far west of the United States, and they got this frequency. Excuse me, got a little bit of a tickle in my throat today. So here's what they observed on the far west coast of the United States. And what they expect from the overall United States is this. So, does the far west coast of the United States fit the rest of the country? So, are they watching TV? Do they have the number of televisions with the same frequency as the rest of the United States? Now, this first table they give me in percentages. In the second table, they give me a frequency. So I'm going to have to calculate the frequency from these percentages. So I'm going to take the 10% and I'm going to multiply that by 600. So out of those 600 observed people, if the number of televisions they have fits what I expect, I should see 60. And I do the same thing with the rest of this. $330, and 11% of 600 is 66, and 8% of 600 is 48. So now I have the expected values and I have the observed values, and I can now conduct the test. So over here, I have the percent. I changed that to a frequency, so this is what I expect. So now let's put our observed and expected in our calculator. So what I observed, I have it written down anywhere. I observed 66, 119, 340, 60, and 15. This is what I observed on the far west coast. What I would expect if the far west coast fits the percentages of the rest of the United States, I would expect, I got a boo-boo here. This is not the observed. That was the expected. Do, 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 do. Apparently have not got it written down on my paper, so I'm gonna have to go back. So we would observe 60. This is what we expect. I am going to get this right, I promise. 60, 96, 330, 66, and 48. So observed 66, 119, 340, 60, and 15. And what we would expect is 60, 96, 330, 66, and 48. So if the far west United States fits the same percentage as the rest of the United States, we would expect to see this number of televisions 0, 1, 2, 3, 4 plus. We would expect to see this number in the right column. We would expect to have 60 families out of the 600 having no televisions. We, excuse me, we would expect 96 to have one, etc. So I'm going to put this data in my calculator. So I'm going to put my observed in a list and my expected in a list. Stat, edit, so we might as well use 5 and 6. So I'm going to put my observed, which was 66, 119, 340, and 60, and 15. And then what I observed was, that's what I observed. What I expect would be 60. I'd expect 96. If the far west, the frequency is the same as the rest of the United States, then I would expect of the 600 families that 60 of them do not have a television. Okay. 330, 66, and 48. All right, so we're good. So now we're going to go run the test. Stat tests. We're going to run a chi-squared goodness of fit test on L5 and L6. Degrees of freedom, we had 5 categories. So we have 4 degrees of freedom. So the chi-squared test statistic is 29.646, and the p-value is 5.776 times 10 to the minus 6. So that's 0.00000578. And then you can see the squared Pearson residuals. We have 0.6, 5.5104, 0.3030, 0.5454, and 22.6875. So let's go back over here and write down our p-value. Our p-value is almost 0. So since the p-value is so low, we're going to reject the null hypothesis. The null hypothesis would be that the far western United States has televisions with the same frequency as the rest of the United States, and that is obviously not true. The far western United States distribution of televisions does not fit the rest of the United States. They are not the same. We reject the belief that the distribution of the far western United States is the same as the American population as a whole. So at a 1% level of significance from the data, there's sufficient evidence to conclude the number of televisions distribution for the far western United States is different than the rest of the United States. I'm not going to do this example. Okay, the second way we can use a chi-squared test is of independence. And so what we're going to do is we're going to look at two different variables, and we're going to try to determine if those variables are dependent on one another or not. Now, I'm not going to actually do any of the squared residual calculations by hand. I'm going to let my calculator do all of those for me. It's just too cumbersome to do them by hand. But if you're doing a test of independence, you're going to be looking at contingency tables, because a contingency table shows the dependence or independence of one variable compared to another. For example, I'm not going to do that one. Getting ahead of myself here. So in a test of independence, we state the null and alternative hypotheses in Word. Since the contingency table consists of two factors, the null hypothesis states that the factors are independent, and the alternative hypothesis states that they're not independent, that they are dependent. If we do a test of independence using the example, then the null hypothesis is, for this previous one, being a cell phone user while driving and receiving a speeding violation are independent. If the null hypothesis were true, we would expect about 28 people to use their cell phones while driving and to receiving a speeding violation. Okay? The test of independence is always right-tailed because of the calculation of the test statistic. If the expected and observed values are not close together, then the test statistic is very large and way out to the right in the chi-squared curve, as it is in the goodness of fit. The number of degrees of freedom for the test of independence is the number of columns minus 1 in your contingency table times the number of rows minus 1 in your contingency table. The expected value of each cell in your contingency table for the expected value is the total of your row times the total of your column divided by the total number surveyed. All right, let's do this example. In a volunteer group, adults 21 and older, volunteers from 1 to, let me read that again. In a volunteer group, adults 21 and older volunteer from 1 to 9 hours each week to spend time with a disabled senior citizen. The program recruits among community college students, four-year college students, and non-students. In the table, there's a sample of adult volunteers and the number of hours they volunteer per week. Is the number of hours volunteered independent of the type of volunteer? So here's what they've observed. Community college students, 111 volunteer 1 to 3 hours, 96 4 to 6 hours, 7 to 9 hours is 48, and they actually give me the row total there, which is very convenient because in a lot of your homework problems, you're not given the row total, so you do have to add that up. So they surveyed 255 community college students. And then of the four-year college students, you can see that they surveyed 290, and you can see the breakdown. And then non-students, they surveyed 294, and you can see the breakdown there. And then you can see the column totals, the total that volunteered 1 to 3 hours, 4 to 6 hours, 7 to 9 hours, and then the total number of people surveyed were 839. Okay, so we need to put two contingency tables in our calculator. we need to put the observed contingency table in our calculator, and then we need to put the expected contingency table in our calculator. And this is the way we're going to do it. We're going to do it in a matrix. So the way that we can get data in rows and columns in our calculator is using matrices. So we're going to use the matrix menu, which is above the inverse button. So second inverse gives us the matrix. Now I have a whole bunch of matrices in my calculator because I was teaching college algebra. I was teaching matrices in college algebra. So I need to delete all those. So I'm going to get out of here. I'm going to go to my memory management. I'm going to go memory management delete number 2. I'm going to go to number 5 matrix, and I'm just going to delete those using the delete key. Delete, 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 delete. All right, now I'm good to go. Okay, I'm going to go back to my matrix menu. Second inverse, that's my matrix menu. The first column in the matrix menu is just a list of matrices you've inputted. The second column we are not going to deal with in this course at all. It's the math menu. And then the third menu is where we're going to put in our tables. So we're going to enter our tables into our calculators using matrix edit. Okay, so I'm going to put my observed values, the number of volunteers that I had in each of these categories, in matrix A. So I do need to tell my calculator how many rows and how many columns there are in this table. So we had 3 rows in this table: community college, 4-year college, and non-students. So we had 3 rows. So the first number that I have to tell my calculator is the number of rows in my contingency table, 3. And when I hit the enter key, it makes the 3 rows for me. And then how many columns did I have? I had 3 columns because I had 1 to 3 hours, 4 to 6 hours, and 7 to 9 hours. So I had 3 columns. And then I'm just going to input the observed data. So we had 111 community college students that volunteered 1 to 3 hours. So I put that in. Then I had 96 who volunteered 4 to 6 hours, and then I had 48 that volunteered 7 to 9 hours. And then I put in the second row, which is 4-year college students. So I had 96, 133, and 61. And then the last row was non-students. I had 91, I had 150, and I had 53. All right, so now that I have that first table in my calculator, I'm going to exit out of the matrix menu and then go back in. Now I'm going to put, now you can see, by the way, you can see that my observed values is now in my calculator. Now I'm going to put what I expect. So it's a 3 by 3, 3 rows, 3 columns. And now I'm going to let my calculator do the calculation for me. So I'm going to do row total times column total divided by total total. So for that first one, let's go back over here. I had, for the row total of community college students, I had 255. For the column 1 to 3 hours, I had 298. So what I do is I take the 255, I multiply it by the 298, and I divide that by the 839. So the row total times the column total divided by the total total will give me what I expect for that particular category. That's what I would expect if it fits what I expect. Okay, so I'm going to go back over there and do that calculation. Okay, so for that first table, we had 255. And then I'm just going to put a times. And the column total was 298. And then divided by the total was 839. So what we would expect if they're dependent on each other is 90.572. And then we just continue. Row total times column total. That second column was 379. Divided by the total, which was 839. That last column, we had 255 as the row total times the column was 162 divided by the total was 839. Okay, so there's the first row, and then we continued on the second row. The second row is four-year college students. We're finding the expected values. So the row total there was 290 times the column total was 298 divided by the total, which was 839. And then that second cell in the second row, we had the row total, which is 290 times the column total. The column total for that one was 379 and divided by the total, which is 839. And now the last row. Last column, excuse me. We had the row total, which is 290 times the column total. Oops, got a boob right there. The column total was 162 divided by the total, 839. All right, and then the last one, we had row total 294 times the column total was 298 divided by 839. Then we had 294, the row total, times the column total was 379 divided by 839. And then last but not least, 294, the row total, times the column total was 162 divided by the total. All right, I'm going to make sure real quick that I did all those calculations correctly. It looks good. Okay, so now I'm going to get out of my matrix menu completely. So I'm going to go second, quit. And then I'm going to run a chi-square test. So when I go to my tests, you have two chi-square tests. The first one this one here we've already done, the goodness of fit. Does your data fit what you expect? What we're going to do now is a chi-squared test. So we're going to do C. And you'll know the difference because it asks you to tell where your observed and expected are in a matrix, so in a table. So I have to tell my calculator that my observed data I put in to matrix A. So this is the way we do this. We go second matrix, and we just hit enter on A. Then expected, we put in B. So we go second matrix number 2, B. And then we calculate. So our chi-squared to statistic is 12.9909, and our p-value is 0.0113. So our null and alternative hypotheses are that the number of hours volunteered is independent of the type of volunteer, and the alternative is that they are dependent, that the number of hours you volunteer is dependent on the type of volunteer you are. So we got a p-value of 0.0113, which is less than our stated alpha of 0.05. If the p is low, the null must go. Based on the data that we have, it appears that the type of volunteer you are and the number of hours you volunteer are not independent, that they are dependent on each other. And that kind of sort of makes sense to me, that the type of volunteer you are would depend on, the number of hours you volunteer would depend on the type of volunteer you are. Okay, I'm going to leave this example to you. It takes quite a bit of work to put it in your calculator. But they gave you the row totals and the column totals, which is very, very, very nice. So you're going to put this data, this table, in a matrix. It has 1, 2, 3 rows, 1, 2, 3, 4, 5 columns. So it's a 3 by 5. You put this data in one of your matrices. So you put what you observed. This is the observed values. And then in another matrix, you're going to put the expected values. So expected is row total times column total divided by total. So for that first cell in that expected value matrix, you're going to put 155 times 57 divided by 400. And you continue. The next one would be 155 times 95 divided by 400. 155 times 127 divided by 400. 155 times 63 divided by 400. 155 times 58 divided by 400. And then you do the next two rows the same way. And here's the values that you should get. Okay, and then I include some of the data from the M&M example that we did. Here is what we observed, and here's what we would expect. So you can actually do a goodness of fit test here. Does what you observed actually fit what Mars says you should expect to get? So this is a chi-squared goodness of fit test. And that concludes chapter 11.